Alright, now let's discuss how electron affinity also varies from the top to the bottom down a group. Is that okay? So now let's look at a generalization. Electron affinity decreases, so our keyword here is EA decreases down a group. So EA decreases down a group. That is from the top to the bottom. So if you are considering a group, so let's take the group 1 elements, lithium, sodium, potassium, rubidium. We can also include cesium and then francium. Is that okay? So it means that the electron affinity for lithium will be higher than that of sodium, and that of sodium will be higher than that of potassium, and that of potassium will be higher than rubidium. Rubidium also will be higher than that of cesium. Is that okay? It means electron affinity is gradually decreasing whilst you're moving down the group. What is the meaning of this variation? So down the group, if we could recall, we said down the group there is what? 1, an increase in number of shells. And what is the implication of an increase in number of shells? An increase in number of shells implies that there is an increase in number of inner or core shells. An increase in number of inner or core shells down the group implies that there is an increase in inner electrons or core electrons. What is the work of these inner or core electrons? They cause electron repulsion. And this electron repulsion brings about a reduction in attraction that is caused by the protons onto the valence electron. And we call this screening or shielding effect. And this increases once you're moving down the group due to the increase in number of shells, which increases the number of inner shell, which increases the number of inner shell electrons. So in summary, the distance from the proton and then the valence electron becomes very wide. And we say that the proton attraction for the valence electron is minimal once you're moving down the group due to the reason that I've stated just now. How will this influence electron affinity? Affinity for an electron is me adding more electrons onto my shell. So if I want to add an electron to my shell, that added electron needs to be accommodated. Add an electron, an additional electron to the outermost shell. It means I need to accommodate that electron. And one gentleman that will help me accommodate that electron is effective nuclear attraction. And effective nuclear attraction is very low once I'm moving down the group. So once I take lithium, sodium, potassium, rubidium, cesium, and then francium, effective nuclear attraction decreases. Is that okay? So ZFA, that is effective nuclear attraction, it decreases down the group. And the moment it is decreasing down the group, it means its influence in electron attraction is very low. So once I add an additional electron, it can be accommodated well in the outermost shell, because the one responsible for accommodating that electron is very low or nowhere to be found. Is that okay? And based on that, electron affinity decreases down the group due to a reduction or a decrease in nuclear attraction for electrons. Is that okay? That is a generalization. Is that okay? That is a generalization. But there is an irregularity in this variation. There's an irregularity in this variation, and I'm going to use chlorine and then fluorine. When you take the group 7 elements, group 7 is made up of fluorine, chlorine, bromine, iodine, aspartame. Is that okay? So in EA, variation down the group, we said EA is going to what? Is going to decrease. What is the meaning of this? It means that the electron affinity for fluorine will be greater than the electron affinity for chlorine. You get a point here? Because electron affinity is gradually what? Decreasing. The irregularity here is that chlorine has a higher electron affinity than fluorine. Chlorine has a higher EA than fluorine. And this is a discrepancy in the trend, because in the trend, we expect the electron affinity for chlorine to be lower than the electron affinity of fluorine, because electron affinity decreases down the group. So since it is decreasing, the affinity of fluorine is expected to be that of what? Higher than that of chlorine. So we expect chlorine to have a lower electron affinity than fluorine. But chlorine rather has a higher electron affinity than fluorine. And what is the reason? Is that okay? One thing that can cause electron affinity to decrease or increase is electron repulsion. Is that okay? Now let's explain this more. In both fluorine and chlorine, we are going to write the electron arrangement for both chlorine and then fluorine. So for fluorine, we have 1s2, 2s2, 2px, 2py, and then 2pz, 2, 2, 1. And then in chlorine, we have 1s2, 2s2, alright, 2p6, 3s2. Then I move on to 3px, 3py, and then 3pz. So here I have 2, 2, 1. Now let's look at something here. If I want to add an electron to fluorine and then chlorine, it will be accommodated by the 2p z orbital in fluorine, and it will also be accommodated by the 3p z orbital in fluorine. Is that okay? Now, the moment we add an electron to this orbital, there's going to be electron repulsion. Is that okay? And once the electron repulsion is very high, it means that attraction that is going to help the added electron to be accommodated becomes very low. Is that okay? So over here, the reason why chlorine has a higher electron affinity than fluorine against the normal trend is that, looking at the size of the 3pz orbital, it is bigger than the size of the 2pz atomic orbital. Is that okay? And so, if we add an additional electron, the repulsion that will take place in the 3pz orbital won't be the same as the electron repulsion in the 2pz orbital. Meaning that since the 2pz orbital is small, the electron repulsion will be very high over there compared to the 3pz atomic orbital, which will experience electron repulsion, but it will be very low due to its size. Is that okay? So due to the orbital size of the 3pz atomic orbital and in the 2pz atomic orbital, electron repulsion in the 2pz will be very high. And once electron repulsion is very high, it affects electron affinity. Is that okay? Do you get the point here? Once electron repulsion is very high, it affects electron affinity. So, in summary, we are saying that between chlorine and then fluorine, according to the general trend, we expect chlorine to have a lower electron affinity than fluorine. But since it is an irregularity, chlorine rather has a higher electron affinity than fluorine. And the reason is that the added electron is going to experience repulsion. The added electron in fluorine is a 2pz atomic orbital, and then for chlorine is a 3pz atomic orbital. The 3pz atomic orbital is bigger than the 2pz atomic orbital due to its orientation. So the electron repulsion in the 2pz will be very high. And once the electron repulsion in the 2pz is very high, nuclear attraction over there will be reduced. Again, in the chlorine, electron repulsion will take place, but due to its larger size, the repulsion will be reduced compared to the repulsion in the 2pz. So even though there is going to be electron repulsion, which is going to reduce the nuclear attraction. The nuclear attraction over here will be better than that in the 2p due to the orbital orientation. Therefore, chlorine will rather have a higher affinity for electron because its nuclear attraction will be considerably higher than the attraction in that of the 2pz atomic orbital in fluorine. So EA generally decreases from the top to the bottom, moving from the top to the bottom down a group. But one discrepancy is for fluorine and then in chlorine, and that is what I've explained as well. Please, if this is your first time visiting our channel, don't forget to subscribe to our channel, like, and then share. If there is any misconception, please you can leave a comment for further discussion. Thank you.